Hello, everyone. Welcome to the workshop. I hope you're all doing well. I can see a few people are speaking in the chat already. So what I like to do is just have everyone say hi and where you're joining from, and just start getting a little bit of chat back and forth going. So this is going to be a new format for Surface Ventures. As opposed to our standard webinars, it'll be a bit more of an interactive workshop. So please don't be afraid to ask questions. This is on nice fundamental material. We'll be going through some applications and everything. So please do go ahead and ask your questions, and we'll try and get to those. Yes, unfortunately, Wrexham's not so sunny, Ben. It's not particularly sunny in Chelmsford here either. Okay, so before I kick off and properly get started, what I'd like to do is release a quick poll question just to ask, what stage of your career you're at. So, whether you're a PhD student, undergraduate, postdoc, or perhaps a more tenured academic. I'm curious about what stage we're at with our audience. Okay, so it seems to be quite a few PhD students here. Okay, so this will hopefully be quite useful for you in your research, and just would like to release another quick poll question as well, just asking whether you currently use surface engineering in your research or work. Okay, so the overwhelming answer is yes. Okay. Yeah, standard weather for Wrexham, Krish. Okay, so let's go on. So, quick overview of the workshop. So, what I'm going to do is talk about what the structure of a standard surface looks like. Talk about why we would engineer surfaces. Give an overview of some of the industrial applications of surface engineering. And then talk about the specific methods that might be used in that. We'll be having a little sort of a bit of an interactive session talking about what type of coatings might be useful for a particular application. I want to discuss the impact of surface engineering in the UK and globally. Excuse me. Then after that, we'll be having a quick Q&A session on the sort of workshop section. And then we'll go to our demo. And then we'll be bringing in Professor Ben Beek from Micro Materials to help answer any of your questions, specifically on the NanoTest platform and the impact methodology. So let's go ahead and take a look at surfaces. Okay, so Wolfgang Pauli said, God made the bulb, but surfaces were invented by the devil, and we'll be somewhat exploring what he meant by that. This is a surface engineering, and surface science can be a relatively complex field. But ideally, we'd sort of say, okay, the surface is, the plane at which the solid terminates. So basically, as soon as we get to, from solid phase to then whatever other media you're in, liquid, vapor, that's it. That's your solid surface, which is great in ideal circumstances, but the actual interactions between the surface isn't just kept to that termination layer there. So, and surfaces have complex structures, which we'll get to in the next slide. So, in a real sense, we could say the surface is the first 2 to 10 atomic layers. But then, oftentimes in surface engineering, we're playing with coatings that could be microns, tens of microns thick. So this is a relatively fuzzy definition, shall we say, of like where, what kind of scales we're playing with, but that is surfaces themselves. So for typical surface layers, we have an actual surface texture. So this could be, there's several orders of surface texture. So, roughness, waviness, lay, which I'm not going to just particularly discuss here, but we have several different layers of this, physisorbed and chemisorbed layers. So these can be things, like, small dirt, debris, oxides, chemical reacted layer, again, can be an oxide layer, can be other things, but just because a material is a solid does not mean it is unreactive. We have a Bilby layer, which is essentially an amorphous layer. Then following that, 1 to 10 microns typically, but this can be different, material dependent. Heavily deformed layer, so when you have any kind of contact, you'll get heavier plastic deformation. Then lighter plastic deformation, a lighter deformed layer, and then you can basically say, okay, well, the base material is untouched. You don't really get very much. That's bulk effects, which we're going to say, yep, we're not interested in for this. So, what is surface engineering? Now that we know what surfaces are, it's the subdiscipline of material science that deals with the surface of solid matter. So, okay, so we got material science. We also have, interactions of solids with other solids. So this brings in tribology as well, which, though I'm not going to talk about in this workshop, will be featured in one of our future workshops and others beyond that. So we have surface finishing, so modifying the actual, the surface roughness, texturing, surface science, so studying the interactions between the surface and any other media that it's interacting with. This could be like for tribology, when you have tribal layers formed by frictional interaction, tribological contact on the surface, and surface metrology, so actually defining what your surface roughness texturing is. So various different techniques used for that, and a bunch of different roughness metrics used for that. So you could say that this is the application of traditional and innovative surface modifications, treatments, or coatings to engineering components to enhance properties. So this is generally an enhansive field, excuse me. So we're trying to add additional properties that bulk materials cannot achieve alone, or to give new properties to bulk material. So presenting cost-effective solutions to practical problems. Okay, so one of the first, so Tom Bell in 1985 launched, I believe, the first surface engineering journal called Surface Engineering. And in his early work, said surface engineering makes possible the design and manufacture of engineering components with a combination of bulk. So this could be, load support, structure, things like that. And then surface properties unobtainable by a single monolithic material. So we'll get into some of the differences between, what our bulk structure is giving us versus what our surface structure is giving us a little later. So I do just want to say as well, guys, if you do have any questions, please feel free to type them in the chat. We'll be having, as I said, several Q&A sessions. I know it's a little early in the webinar, but I just wanted to say, please go ahead and type your questions if you have them, and I'll get to those. Sorry, back on to terminology. So surface treatment or modification. So effectively whatever technique that is used to change the surface properties without necessarily altering the final dimensions. So these could be things like, shot peening, flame hardening. The shot peening might give you some dimension changes just by the bombardment of things on the surface. So, basically surface hardening is kind of the main thing that we cover in that. Surface coatings, so deposition, growth, or co-deposition of additional materials to modify the surface, essentially adding another material to the surface to change the properties of the overall part. Oh, and surface texture, so patterning that can add to the properties of surface texture. Multiple techniques for this. Actual machining itself, you can have laser surface texturing. If you could look back at some of Surface Venture's previous webinars. We had Professor Carsten Garchot who had a wonderful webinar on laser surface texturing. So I would encourage you all to check that out. So why do we engineer surfaces? So two main things. To achieve a different surface property is the primary function. So I mean, effectively look at that as the bulk material is just what's holding, what's supporting, what's carrying the surface, but the actual surface itself is the primary function, or the primary function of whatever the device is. So generally with that, you will need a bulk material that is strong, stiff, tough, in order to provide the correct support for that. But then the actual material, the surface itself, is the primary driver for that material. Excuse me. And surface property is protection. So this is often in the case of coatings, where we have, again, coming a little bit into the tribology, but we have components that are existing in extreme environments where we need, friction resistant or friction reducing, wear reducing coatings. Could be for actual physical contact itself, where we might have different types of wear occurring, abrasion, adhesion, erosion, fretting, or looking at coating structures that are chemically resistant. Okay, I've got a question there. I'll just mark that, and I'll come to that in the Q&A section. Thank you very much. So having chemically inert surface layers as compared to what could be a reactive surface. So a few examples of where the surface property is the primary function here. So telescope mirror. So primary thing for a telescope mirror is to have excellent reflectivity. You want to capture, especially for deep space observations, you need extremely good reflectivity to capture as much of the light as possible, to try and direct that. And shape as well is important, of course, but that is handled by the rest of the material. But you want to direct as much of that light towards your typically CCD sensor, just because it's these are very faint objects. So there's that. Brake pads is another one. So this is generally with tribology, we look at applications where we want low friction, but brake pad is an area where you'd really not want low friction. You want high friction. You want to be able to stop within a reasonable amount of time, but we want low wear. We want to be able to say, okay, we don't want our brake pads wearing out too much. And because of the speeds that are traveling at, these brake pads can heat up quite a lot. So we need good stability over a wide temperature range. And the secondary property is for it to have the right shape, for it to have the correct surface structure. So this is where roughness comes in quite a lot. Machining tools, excuse me. So again, this is another application where high hardness is key here. So if you have a high hardness surface, it is less likely to plastically deform. Therefore, your tool life should increase. But we also need abrasion resistance, and we also need oxidation resistance, because once again, prolonged contact of tools creates high temperatures, increases the likelihood of oxidation. And then these coatings as well should be able to conform to the surface of the tool that's already there in order to maintain the right shape. Then coming on to semiconductor substrates. So again, primary thing here is being as smooth as possible. So having an extremely conformal coating, so absolute smoothness. and freedom from any defects. So this requires a really well-controlled coating process. The secondary things being strength. So you want to be able to support that typically quite thin coating in terms of semiconductors. And then some applications may require different electrical properties, which is something that the substrate can do. Okay, so coming on to surface properties as protection. So we have a little diagram here of some corrosion of different materials. You can quite clearly see that cemented carbide right there, pretty much untouched by our corrosion versus our two different metals, which demonstrate quite severe corrosion there. So corrosion-resistant coatings is a big thing. Surface treatments as well for protection. Polishing materials for fatigue resistance is the one thing you don't want any crack propagation occurring. This is true with coatings as well. We want to make sure that they're quite fatigue resistant, because if you start to damage your coating, you can have your coating delaminate from the surface, and then you begin to lose the benefit of even having a coating in the first place. Polishing ceramics for strength and erosion and wear resistant layers. So this is where mechanical property optimization is key for this. So looking at measuring the mechanical properties for this, but we'll come on to that a little later. But some of these processes themselves might change the actual surface state. That's not to say that any change you make to the surface can affect its structure or state as well. A lot of applied stresses work harden materials. Some materials work harden, typically for various steels. It depends on their steels and other metals, depending on their structure, as to whether they work harden. You can actually changing the actual topography of the surface with erosion and wear accumulation, fatigue initiation, the beginning of cracks, as you said before, corrosion, so the change, smaller localized areas of chemical reaction where the material is being removed due to those chemical reactions. And this is the beginning of, or could be the beginning of failure of the bulk material. So initiating at the surface and propagating deeper into that. So this is where surface properties are extremely important. So there are a bunch of different areas in which surface engineering is useful, as we've covered. So there's a few other ones of those. Data storage, sensors and transducers, optical devices and displays. Decorative coatings as well is a big one that isn't talked about quite so much, but applying coatings to different parts to make them shinier, change color, friction and wear control, thermal protection with extremely thick thermal barrier coatings. There is a lot that can be done. And a lot of industrial applications for these. So we can go through quickly some of these here. I have some other examples as well in these other slides. So in aerospace, abradable coatings for seals, wear-resistant coatings, and particularly high temperature is required here. And then getting into, as well, more space, erosion resistance in materials is extremely important. As you get higher up in the atmosphere, you get more likely to have atomic oxygen, which can erode materials. So power generation, so intermetallic compounds for high temperature oxidation, corrosion protection, oil and gas, erosion and corrosion protection, extremely important here. Construction engineering, so this is where corrosion is a big deal. So this is where you'll have a lot of galvanized coatings. Space and satellites, once again, so thermal control, baffles, road transport, so coatings for bearings a lot of the time here, ceramic coatings for brake discs, as we've already covered, electrical coatings. So again, conductivity here. Textiles, this is, laser engraving, corrosion and wear protection for print rolls, and biomedical, so bond coats, non-stick surfaces, surfaces that can kill any kind of bacterial growth, extremely important. So for oil and gas, quite a few things. So as I mentioned, erosion and corrosion it's a big thing here. So essentially the sea with its salt content is extremely corrosive, that in addition to, sand carried through pipelines. So this presents synergistic wear, which is quite difficult to deal with. So you need to have quite a few things going on in it with your protection in order to be able to make your materials survive in oil and gas environments. Automotive, so quite a few things here. So surface hardening, so sections for pistons. You could have different coatings there, things like diamond-like carbon for wear resistance, low friction, coatings for bearings as well throughout the automotive structure. Paints as well, so protective paints is another big thing. Computer communication and consumer electronics. So these would be things like polarizing lens coatings for screens, things like your frying pan there, Teflon PTFE coating for non-stick. Last thing you want is for your whatever your food is that you are frying up to stick to the pan. Screens, so these coatings or glasses specifically surface engineered to have both impact and scratch resistance, which can be quite a tough thing to optimize for. Biomedical, so this is where materials are chosen because they need to be able to not provoke an immune reaction within whatever environment that they're in. So for things like knee replacements, hip replacements, things like titanium are chosen because you can begin to get bone ingrowth into the actual implant, so it will become a part, or at least more of a part of your body's structure. And of course, we don't want to, produce any kind of immune reaction, because then you're going to get rejection of your of whatever you've put in there. Okay, so here we have a nice diagram here of hip implants. So in addition to the actual titanium itself, there's a few different things. So looking at metal on metal hip implants are quite bad because of the amount of wear debris generated, and you're releasing a lot of metal ions into your body. So things like the ball material and acetabular cup, these are chosen out of different materials. The acetabular cup typically being a polymer, the ball being cobalt chrome a lot of the time. So these mixture of materials and optimization of the surface in order to produce low wear, you want that hip to feel like part of your body as much as possible. Aerospace, once again. So I got some examples of some coatings for aerospace a little later, but a lot of the time these are quite thick oxide layers because they need to have, it's like good temperature resistance, as well as having specific frictional properties, erosion resistance, as well, corrosion protection, especially for aircraft that are operating at lower altitudes over the sea. That salt spray can be extremely corrosive over long periods of time. And now we come on to the sort of overview of different surface engineering methods. So we'll begin with surface coating. So these we can categorize these into generally three different types. So electrolytic, so anodizing, plating, and PEO, so plasma electrolytic oxidation. So essentially growing oxides on the surface. So, excuse me, typically these oxides are quite protective. So essentially we're taking advantage of the material's tendency to grow an oxide to further protect it. Fusion, so essentially fusing between two elements, essentially with high temperature spraying and weld coatings. So we're using high temperatures here to fuse two materials together. And vapor phase, more where sort of my specialism lies. So my project was in producing various different types of diamond-like carbon coatings, so different thicknesses with different surface roughnesses, with different dopings, and then analyzing the tribological properties of those on various length scales. So there are a number of different materials you can coat by PVD, so physical vapor deposition, where it's much more of a line of sight coating process. Versus chemical vapor deposition, which you're not as limited by geometry, but the temperature requirements are different. You have to have a much more temperature-resistant material, unless you're using plasma enhancement or plasma assistance. Again, we can talk about this for hours and hours. So quickly move on to some of the other types of surface modifications down at the bottom of this diagram. So for leaving the composition unchanged, so typically this is where we are modifying the surface mechanical properties. So things like shot peening to impart stresses into the surface in order to harden it, flame hardening, induction hardening, laser and electron beam hardening. So again, hardening this, but by actually transforming the surface by either by diffusion or diffusionless transformations in order to change typically the type of phase that's present at the surface. So things like martensitic transformations, which is a diffusionless one. Melting, which is a MIG weld, again, or actual and final category here, changing the composition. So ion implantation, so essentially driving ions into the surface in order to harden it. So things like adding boron into the surface can be a good hardening agent, and then thermochemical. So carburizing and nitriding, so essentially using their large vacuum methods or plasma methods in order to diffuse carbon or nitrogen into the surface in order to create a different a layer of different composition that will have higher hardness than the unchanged surface that was there before. Okay, so this is where I would like to open it up to a little bit of discussion here. So we have different surface modifications and treatments for various different things. So we have a steel pipe for transport of rock in a mining operation, drill for producing holes in mass-produced printed circuit boards, cylinder bore in a petrol engine, and skis and sledge runners. So we get a few suggestions for what type of coating modification treatment you might recommend for the steel pipe. Get a little bit of a few suggestions in the chat, please. What do you think? We sort of kind of covered some surface treatments here, so I'm sure you all have some good ideas. Okay, so I think for this CVD, PVD, okay, yeah. So a lot of this, so I mean, for transporting rock, we're going to need mechanical properties, which CVD and PVD, yep, sputtering could be a good one. Okay, so let's think about the drill for producing holes. So with that, if we're drilling, what kind of properties do we need? Mechanical properties as well, I think. So what do you think on that one? Same thing for the probably for the cylinder bore, petrol engine. So a little different for the skis and sledge runners. So what do you all think about that one? Wear reduction for the drill bit? Yes. Yes, we want good wear reduction there. PTFE, yep, for the skis. Excellent. Excellent. So let's go on for some of this. So some of the actual suggestions here. Yep, so abrasive wear resistance, but for things like a PTFE is hazardous. So polymers can break down, yes, but the PTFE or the Teflon specifically used for coatings, well, at least in terms for coatings used for any food safe things, this is a safe polymer. PTFE itself for the actual skis, non-hazardous. I'm sure there are, this is the one thing with polymers, you need to make sure that they're safe. But anyways, moving back onto this. So for our steel pipe for transport of rock, yes, we would be able to get the properties that we require from PVD, but with the amount of material being moved, we want something a little bit thicker than what a typical PVD coating can give. So high velocity oxyfuel cement coatings, ceramic and metal mixes. So tungsten carbide cobalt is a good one. So having usually fluorinated waxes are on top of the PVD and is the more hazardous component. Yes, that is true. So again, this depends on the exact preparation of the PTFE. But moving back onto this, so PVD, perfect for drills. So this is the sort of thing we're looking at. Ceramic coatings. So if you've ever seen any gold drill bits, those would be your titanium nitride, titanium aluminum nitride, titanium carbonitride, all of these giving good hardness up to a high temperature, good wear resistance. So basically allowing our tool to remain in action for as long as possible and keeping the geometry there. Tetrahedral amorphous carbon, another one, yes. Another great one. We do kind of see that the tetrahedral amorphous carbon. I think typically more applied on kind of medical, or at least any of the diamond-like carbon coatings for drills. A bit more on medical drills, just because you can have a little bit more control of that carbon than you can with a really high high part process for typical drill bits. So cylinder bore, thermal and wear resistance. So plasma electrolytic oxidation, hard anodizing, another one. And then, as we said, skis and sledge runners need to have good properties at low temperatures. So polymer coating, like PTFE. Okay, so coming on to the economic impact now. So annual cost of corrosion worldwide is, at least at the time that this was done, so a couple of years ago, but 3% of the world's GDP, which is huge. Wear itself in the US alone, about $2 billion per year, which is just a huge amount of money that is being lost when relatively small amounts of work can go into optimizing properties for materials. You mean by a medical drill? Sorry, I'll stop quickly and do that. So by drills for surgery. So typically, a drill for say, standard things like, like metals, these tend to be quite large because the actual screws and bolts that you want and the holes that you want are far larger, whereas a medical drill tends to be a lot finer because this is the sort of thing that's taking, it's in surgery. So this could be drilling into bone, for example. So that's what I mean. I just mean a finer, smaller drill bit. That is all. So coming back to corrosion. So yeah, so aircraft industry, at least in 2000, $13 billion per year. Oil and gas, 1.4 billion. So these are huge sums of money that are being lost to things. When we can apply, then there are technologies that exist, as I've talked about, that can reduce the amount of this money lost significantly. Impact in the UK. So there's this. Some of you may be aware of this great report by the Surface Engineering and Coatings Special Interest Group, Time for Strategic Change. So talking about the UK surface engineering and advanced coatings industry. So UK coatings themselves worth over £11 billion, but further go on to affect products worth over £140 billion. This report talks about the various environmental concerns with using other heavy elements and the societal benefits, and gives quite a few great examples of where coatings can be better optimized, and just discusses at least the state of the industry when this was written. Though 2014, I still think a lot of the recommendations are extremely important and valid, and because it's freely available on the internet, I've gone ahead and grabbed that for you. So in the handout section now, you'll find that report. So please feel free to go ahead and download that. If you do search, Time for Strategic Change, Surface Engineering Report, you will be able to find it quite easily. It's free to download, so that is there. Okay, so come a bit more on to the practical part of this. So we have properties for I've talked quite a bit about properties for protective coatings. So what's actually important here? So typically, in terms of corrosion resistance, it tends to be the actual composition itself of the coating that is the important thing, because the actual elements and constituent phases there, although surface roughness is a big thing as well. The typical elements and phases are what defines the chemical reaction for corrosion. But for other types of materials, mechanical properties are key. So this is, these are things like, hardness to elastic modulus, as that feeds into, the relation of hardness to elastic modulus that's used for prediction of wear resistance and frictional performance in tribological coatings, toughness, resistance to fatigue failure. So what we have here is an image from one of my papers. This is a silicon-doped diamond-like carbon, which we'll talk about a little bit later, is a coating we'll revisit in the demo video, or a coating similar to that in the demo video, excuse me. So this is an impact failure on this. We can see some of the cracking there. So how do we go about measuring this? Mechanical properties themselves, typically for hardness to elastic modulus, we would use instrumented indentation. So again, so various different geometries of indenters can be used, but typically, we're applying a load to a surface in order to induce plastic deformation, and then we are measuring what the projected contact area of that is. So typically, the analysis method for this is the all over far method. So again, I don't want to talk, too much on this, just because it's, there's a great deal of information out there anyways, and then there's also the ISO 14577 standard, instrumented indentation, which talks about 10% of your coating depth in order to get an estimation of what your coating mechanical properties are without getting any substrate properties in there. So that's how you would get hardness to elastic modulus. But nano indentation is it's a relatively slow, where it's quasi-static. So essentially, you're slowly deforming your surface, with lower strain rates, so we can get our hardness modulus and various different wear ratios, as I talked about. But we can look at other test techniques, like this woodpecker here with nano-impact, so a much more dynamic technique, with a much higher strain rate with repetitive impacts. So we can look at, with lower loads, fatigue failure or coating toughness itself. So trying to induce failure, induce cracking on the surface in order to study what the impact resistance is, or have a test that mimics slightly different conditions rather than the slower nano indentation test. Not to say these two techniques provide two completely different sets of information. So it's not like impact is suddenly better than nano indentation. The two, the information between the two of them, you should be able to, you link them. You sort of say, okay, well, the nano indentation feeds the information that I can get from the nano impact. It's not just, there is no one magic technique with this. So damage mechanisms. So a lot of this will be, it's we can mimic particle erosion. So you have nanoscale, microscale impact depending on the load there. So we have different types of cracking on the surface: cone cracks, lateral cracks, median cracks. So essentially, this is all as a result of the higher strain rate plastic deformation that's going on. So we can use this impact testing to try and understand the type of damage that we see under this. Look at whether it's deformation, inducing plasticity or fracture. And this is very beneficial for advanced ceramic coatings, for thin films, to try and improve their damage tolerance in some specific environments, which I'll talk about in a moment. So one of the main pieces of equipment that is able to do this type of testing is the Micro Materials NanoTest platform, the nano-impact system. So it takes their standard side-on geometry indenter and uses an electromagnet in order to impulse the indenter into the surface. Typically, the actual retraction distance is fixed, and they'll vary the load of this. So you have the nano-impact technique. You're able to highly tune the test. You can changing your load is effectively changing how much energy you're imparting onto the surface. You can change your indenter geometry, whether that be something a spherical blunter indenter versus something like a cube corner if you really want to fail your coating quickly. So lots of different options in order to explore. So let's look at a bit more of a practical example before we get on to the demo in a moment. So we have a thermal barrier coating here on the vanes of this turbine. So typically the structure of this, the actual bulk material, would be a superalloy, generally nickel-based, something like Inconel, various grades of which. There's a thermally grown oxide bond coat, essentially acting as our adhesive layer, and then a top coat produced by PVD. We have you can see a nice columnar structure there. It's quite typical of PVD coatings. So in more extreme environments, for more military, where could be dusty environments, you're going to get a lot of erosion, a lot of particulate matter coming into the engine. So that's where you really want to make sure that you don't want to have failure of any of those vanes, because these operate at extremely high tolerances, extremely high speeds. So you could, you're risking an engine failure with that. So we can look at nano impact of these. So what we have here, the graph on the left, this is our actual erosion test here. So we have an as received coating versus two various different heat treatments, 1100 and 1500 degrees for 124 hours respectively. So we can see is quite clearly our heat treatments are detrimental to this type of coating. I have a little schematic here of what some of these coatings look like and our repetitive impact. So what you can see here is that our nano impact, as opposed to performing a sometimes difficult to set up erosion test, we can do a nice standardized impact test in order to get pretty much the same thing. So our probe depth can correlate with our mass loss here. So you can see that our as received coating performs far better than the two heat treated ones. So what's going on with the heat treatment? So what you can see is, with this type of coating where it's quite columnar, at these high temperatures, you're beginning to just sinter the columns together. And this reduces its erosion resistance, really leading to greater material loss. And we're able to tune this test here so that we can match the size of the eroding particles, or we can also you can also tune this so that the actual impact geometry matches the size of a single column. So we're able to really modify this test here. Another example here, we can look at coating damage and machining. So we have on the left flank wear from a tool with over various different lengths of cuts, increased time in cutting. So flank wear, essentially as the geometry of the tool is changing, you're losing material from that. And we're able to do impact tests in order to bring out very much the same type of behavior. Our aluminium chromium nitride is performing far, far better than our titanium aluminium nitride. This, where we see quite similar behavior, are sort of, we get sort of a fatigue plateau, as it were, with these repetitive impacts. But then titanium aluminium nitride is just going off, increasing depth, increasing wear. So this is quite nice because of an interrupted cutting test. You're able to mimic that with the nano-impact. This isn't a constant cut. This is specific sections of a drill that are impacting and then cutting into the surface. So very good. I'll come to the one drills in detail in a moment. Thank you for the question, Peter. I've got one more example here. So you can correlate tool life for this aluminium titanium nitride. So various different structures of coatings here, which I'll come on to properly in the next slide. But we have quite a thick coating here on cemented carbide. And what we can see here is we have a difference in impact depth with, or difference in impact depth we can correlate to tool life, the number of cuts possible with each. So what's going on here in terms of the structure we've got is different layers. So one thing with types of impact testing is that layer structures are far better than one single monolithic, a single phase coating, single material coating. So the more layers you have, the less likely it is for cracks to propagate throughout the entire coating structure down to the substrate. So this paper pushed it a little bit to extremes, taking it from 1 to 4 to 300 layers. So there is I'm sure a happy medium in these where you want to achieve a good tool life without drastically extending the time required to prepare your actual coating. So that's sort of it for the workshop section of this, but please don't leave yet. We still have the nano-impact demo to show you, but I want to go on to just have a few announcements. So I've got a nice QR code here for our next Surface Ventures webinar. Professor Albano Caballero from Coimbra University talking about new insights in transition metal dichalcogenides coatings, TMD coatings, excuse me. So please go ahead and visit that. That's also on our website, surfaceventures.org. We have our next workshop coming up, so a little bit more on tribology. So it'll be a similar format to this with a demo, but with a tribometer and AFM, atomic force microscope demo. So please do go ahead and scan that. Again, if you visit our website, you'll be able to sign up to our mailing list and more information, and there will be a bit more information released on that later. You can also find us on LinkedIn. And I'd also encourage you all to please visit our website and also look at the website for Micro Materials. Check out some of their test techniques, products, technical notes, and related publications. So now come on to a couple of the questions. So I had one here. So in studying the tribological properties of frictional data happens to be the outcome of surface properties. How relevant is it to judge the bulk material relying on that data? Is there a way we can nullify the surface roughness role in frictional properties? So that's quite an interesting question there. So in terms of this would be more a case of judging the bulk material relying on that data. So that's very much a case of to what length scale does your plastic deformation propagate into the material. So if it propagates far enough such that you're deforming the bulk, then yes, absolutely, you can then sort of say, you are judging a composite of both the coating or technique with the bulk material. But that's very much a case of pick your length scale of testing. Be sure try to choose your contact pressure that you pick for your tribological test carefully, so that you're only testing one of the things. But if you're doing particularly long tests, of course, be aware that you are going to wear your coating, and you are eventually going to begin to wear your bulk material as well. And is there a way we can nullify the surface roughness role in frictional properties? With reduced surface roughness, yeah, you're going to see that. I mean, at least on the macro scale, at least you're not going to get sort of much larger wear particulates generated, say from abrasive wear, where you're then going to get from, instead of our 2-body wear, 3-body, when you're generating additional wear particles. But as you jump down the length scale from micro to nano, this surface roughness becomes massively more important, to the point where it is highly unlikely we will ever be able to nullify that surface roughness role, just because the actual scale of interactions is far different. You can look at larger scales where our actual contact, real contact area for macro is far smaller than what our projected area is going to be. But we're deforming multiple asperities, multiple elements of the surface, versus nano, where where it's effectively a one-on-one, one asperity on asperity. So that's why you can't really nullify it at that point. Have I examined worn drills in detail? So no, my work never really focused on worn drills. My PhD work was very much on kind of a more fundamental study of coatings across length scales. So yes, my work could be applied specifically. I would say that the impact sections of my work for diamond-like carbon coatings would be very helpful to studying drill performance, as well as the mechanical properties as well. I investigated using a slightly different method of indentation, so partial loading, so you're able to map how the mechanical properties change, so the coating structure. So you get a nice peak, and then you can see how the mechanical properties drop off towards more substrate effects. So that could be quite useful. But in terms of what I've actually looked at myself, no, never studied worn drills. But yeah, thank you. Let me just check back that I have not missed any other questions. So are nano tribological properties different from that of the bulk? So as I talked about, yes. So in terms of nanotribology, that's where surface roughness is far more, surface roughness, as well as surface chemistry, humidity interactions in terms of meniscus effects. So this is the realms of atomic force microscopy, scanning probe microscopy. So where, once again, as we're reducing in scale, we need to reduce the scale of the contact of our instrument accordingly, and increase the sensitivity. So we'll talk a little bit about that in the next workshop. So I have another question here of oops, sorry, let me just bring that up. So what do you think the best surface preparation methods of polymers for demanding conditions, including well-lubricated contacts? Perhaps unspecified question, but anyway. So methods of polymers for demanding conditions, including on lubricated contacts. The one thing is with polymers is that quite a lot of the time they can be self-lubricating. So this is very much polymer dependent. It depends on the particular deformation mechanisms of whatever polymer it is you're working with. Okay, got quite a few questions. So we're coming up to an hour. So I'll try and answer those questions there. And we'll have another Q&A session afterwards, and then we'll get to the demo. Okay, so polymer dependent. So you can, of course, add other things into the polymer structure, different types of nanoparticles, in order to do that. But you can also, you can add different coatings to polymers, but the one thing to be aware of is the thermal limits of the polymer that you're working with. So this is where things like microwave CVD is particularly important. You can put diamond-like carbon onto polymers. You just need to be aware of your cycle times. You don't heat up your polymer too much. So I'd probably say, in terms of if you want really, really increasing the hardness and wear resistance of your polymer, that's what I would choose. So can the same indenter be used in nano-impact? I think that is in micro-impact versus nano-impact. Yes, you can do that, but I'm sure we'll talk about that a little later in the demo, or after the demo, sorry, in our second Q&A session. So I have another question there. How can one distinguish between static and kinetic friction and at nanoscale? So this would be so static and kinetic friction. So this is where your sort of scanning speed is probably going to be key. So static and kinetic friction at nanoscale, as opposed to your sort of more macro scale, where it's amount of friction you need to overcome to begin movement. At the nanoscale, it's more going to be a case of adhesive or interfacial coefficient of friction versus plowing friction, just because of the way the deformation works. So that's more where you're doing, slow ramping scratch tests is quite good, or extremely low load scratch tests repeatedly. So then you can basically look at your data and go, okay, there's the plowing component, can get rid of that. Or you can extrapolate your data back and then go, okay, here is what the interfacial component of friction is. So this is something I talk about in my thesis, which should be online in probably a few days' time. And also, please be on the lookout for a future paper from me, which will talk about this very thing. Okay. Another question there. What are the most important substrate considerations for successful application of thin tribal coating? So optimizing your surface roughness, being aware that for thin coatings, you're typically PVD, CVD coatings, which are going to bring up the surface roughness. You can modify the roughness of the coating after preparation, but that's not typically recommended. You typically want to prepare your surface roughness and then say that for a very optimized coating, the roughness of my substrate will be the roughness of my coating. So there's that. And then in terms of actual coating preparation itself, cleaning. I mean, they're typically these two coating processes have a plasma etching step, but you probably want to do an acetone, an ultrasonic bath before drying with a lint-free cloth, so you make sure there's nothing going to be underneath your coating. So yep, just take a lot of care with your preparation. We'll do these two questions and then we'll go on to the demo. So we know the reason behind doing heat treatment of the thermal barrier coating. So it's not necessary. So the heat treatment is there to mimic the kind of conditions that you see in engines. So these engines will run extremely hot for an extremely long amount of time. So the reason for the heat treatment is in order to mimic the actual engine conditions. So we can sort of say, here's the ideal coating as received, but we want to be able to have some kind of lab method in order to test, what is the performance of this coating, when it's actually been tested. Typically recovering these things from engines is costly and quite awkward to do. So, a nice bit of heat treatment is able to mimic that quite well. Okay, does the surface roughness and orientation of surface asperities affect the affinity of lubricants to get adsorbed onto the surface? So that's all going to be to do with, so there's a little bit of, I'd say, lubricant entrainment itself, so it's going to depend upon the viscosity of your lubricant, but the actual adsorption itself, so long as your surface roughness isn't too extreme and you are able to entrain your lubricant properly into the contact, I'd say there's going to be very little little difficulty in getting the actual lubricant to adsorb. Okay, so what I'll do now is I'll move on to the demo. Okay, so I got 15-minute demo video here, and then we'll do other questions, some ones specific to the nano-impact platform. Okay, here we go.
Hello, my name's Adrian Harris. Welcome to the Micro Materials Applications Laboratory. We'd like to introduce you today to micro-impact testing. Before we launch ourselves into that technique, I just should introduce you to the instrument itself. I guess that a lot of people are going to be unfamiliar with the instrument. So this is a NanoTest Vantage instrument. It's a multifunctional instrument. It can perform nano indentation and micro indentation for measurement of hardness and elastic modulus of materials. It can perform scratch testing and wear testing. It can perform impact testing, which is what we will look at today, and also a multitude of other tribological techniques. The other thing we can do is we can actually perform these tests in different environments. So we're not restricted to just working under ambient conditions. We could actually submerge samples in liquids. We could test samples in controlled humidity environments. We can heat samples up. We can cool samples down, etc. So we can replicate a wide range of real-world engineering scenarios. The instrument itself is a 2-load head instrument. Covers a very, very wide load range. So this is a low load head that goes from basically 0 up to 500 millinewtons of load, and this is a high load head. It takes us right through to 30 newtons. And both of these 2 loading heads actually can perform all of those measurement types that I've introduced and work across all of those environmental conditions as well. The other thing that's important on the instrument, of course, is the optical microscope. And so that allows us to identify and locate particular regions of interest on a sample, and then the sample stage system will automatically replace that sample from the microscope to whichever of the measurement heads we're using with submicron precision. Okay, we can then perform the test, return back to the microscope and investigate the test site. So, onto the sample that we're going to look at. This is the sample we're going to use today. It's a DLC, diamond-like carbon coating, on a steel substrate. I think it's about 4 microns thick, this one. So here we've just got one sample mounted up. It's a dedicated test piece. But we're not restricted to working with just one sample at a time. We can work with multiple samples simultaneously mounted, and they can be of differing dimensions. So clearly here what I've got is 3 coated metallic samples, and I've got a bulk ceramic sample here, which is 3 or 4 millimeters, about 4 millimeters thicker than the metal samples, and that's no problem for us. We can mount all of those samples simultaneously on the instrument, reference the desired test start point on each of the samples using the optical microscope, define the experiments, and then the system will automatically run the tests on those samples one after the other. Perform tests on the first one, then move to the next one, perform the tests on that one, then on to the third one, etc. With no user intervention necessary. Let's put that one to one side. And then we have here just an example of some engineered components. So these are not dedicated test pieces. These are real automotive engineering components with quite a complex geometry and a particular location on them that needs to be tested. That's no problem. We can mount one or several of these as well and access exactly the region of interest. So it's a very flexible system in terms of what we can put on it. So back to our sample of interest, which is the DLC coating. Very, very simple to put that on the instrument. We just pop it onto the sample plate receiver like this, in front of the microscope, tighten up that screw, and basically we are now done with the hands-on side of the setup for these tests. We can now pretty much concentrate on what's happening on the computer screens. So if we come to the computer screens, we've got two windows of interest here. One of them is the main NanoTest software screen, which is a nice, intuitive, simple interface to use. And the other one is the microscope image screen, so we can actually see the surface of the sample here on the microscope screen. So this blue box here around this microscope position just tells us that currently our sample stage system is at the microscope. You can see there are various other measurement stations available on the instrument depending on what the configuration of the instrument is. So this instrument, as we said, has both the low load and the high load heads. Today we're going to be using the high load head. Let's configure our test. So the first thing we want to do to configure our test is to identify a suitable test location. So as I said, we've got the microscope image here of the sample surface, and we can actually manipulate the sample around in front of the microscope using the sample stage control screen here. And we can manually drive stages around, okay? We can move the sample towards and away from the indenter to achieve focus. Or we can just simply use the point and click system. So wherever we click, gets pulled to the crosshair, and we can select that point for measurement. So basically what I'm looking for now is a region which has got no obvious damage pre-existing at it for our test to take place. And this looks as good a place as any to me. So once we've selected the test position, we can click on quit, and exit that sample stage screen. And now we're on straight away to defining the experiment. Okay, so we go to experiment, we go to impact, and we go to define new schedule. So let's go to our first menu here. We select the experiment type. There are a variety of different tests that come under the name impact. The one we're actually doing today is called multiple impulse. So multiple impulse test actually involves repetitively accelerating a sample probe at a sample surface, a test probe at a sample surface, and then pulling it away again. So we're going tap, 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 tap on the sample surface. You can understand why in the past we've actually referred to this as a woodpecker test. And what we're doing is we're continuously monitoring the depth of the probe as those repetitive impact events take place. So we can define various important elements of our test. And the most important elements, we won't go through everything in detail now, probably the most important element is the load that we're going to use. Now, we already know a little bit about this sample, and we know that 1,500 millinewtons, 1.5 newtons, actually should lead us to some quite nice failure events. Another important thing is how long we're in contact with the sample surface and how long the probe is out of contact with the sample surface. And we define that using this impulse control on and impulse control off periods. So they're both set to 2 seconds. So what that means is that the probe will be released and be in contact with the sample for 2 seconds, and then the probe will be removed from the sample for 2 seconds. And that will take place repeatedly for the duration of the test, which we set here, total sampling time. So normally our tests are between 2 and 10 minutes, something like that. For this demonstration, we'll keep it to 180 seconds, so 3 minutes. And the final thing of significance, perhaps, is the acceleration distance. So we normally set that with micro-impact testing to 20 microns. You can set it to longer or shorter, depending on what you want to achieve. But typically, we use 20 microns. So basically, what will happen is the probe will be accelerated over a 20 micron distance with 1.5 newtons of accelerating force. So it hits the sample surface, will stay there for 2 seconds, will be withdrawn, and then that process will be repeated 45 times. That's a 4-second total cycle time and 180 seconds total sampling time. So actually 45 impact events there. And if we wanted to, we can repeat that test multiple times. So we could say, maybe I want to do 3 repeats and I want to space those maybe 100 microns apart or something. But for the sake of the demonstration, we'll just stick with 1 repeat. Once we've defined the experiment, we simply give it a results file name, and we will just call this 1500 millinewtons times 1. Okay. Click OK. And then, this is an important thing here, we add it to the schedule queue. And what that means is that that one experiment that we've defined it can be run alone by itself, or it can be one experiment of multiple experiments that form what we call a schedule. So what we could do now, if we so wanted, if we had more than one sample mounted perhaps, we could go around this loop again, define the test that we want to perform on sample 2, go to this button here, define start position, move the sample, move the sample 2 in front of the microscope, choose the start position, and then simply select the results file name and add that to the queue. So what would happen then is sample 1 would run, and then when sample 1 is finished, the sample would automatically be swapped for sample 2, and the test would run on sample 2. But as I said, for the sake of demonstration, we're just doing 1 experiment or 1 sample. So we click on finished, and then we're ready to start the test. So at this point, all we have to do is go experiment, impact, and then run schedule. We have the option to delay the start time if we want to. There are sometimes reasons we might like to do that, but today we don't need to. We can just start right away. And so now what will happen is the sample will be automatically repositioned from where it currently is at the microscope to the appropriate test probe, and the test will commence. Okay, so the instrument is now just placing the indenter on the sample surface to take a reference of where the 0 point is, where the actual starting surface is of the sample. Now it's setting the requested load. So what it's doing is applying this 1.5 newtons of load that we specified. So the probes in contact are just ramping up to 1.5. Okay, and here we go. The impact tests begin. So impact 1, impact 2. There it is. Okay, and as you can see, with each subsequent impact, the probe is getting slightly deeper into the sample surface. So we're about 5.2 microns deep now. So 2 seconds in contact, 2 seconds out of contact. Okay, so depth continues to increase. Normally, a very, very abrupt failure would appear as a large increase, a large change in depth between one impact event and the next. So depending on how sudden the failure is, the scale of the difference in terms of depth between one impact event and the next will change. So this sample is kind of somewhere in between, a brittle and a more tough response. So there we've got a fairly significant increase in depth, and there we go. So this is the beginning of our impact failure. Okay, so there it goes. So what we tend to say is here's some events of initial plastic deformation. This we tend to refer to as our fatigue period. Okay, and here is the onset of the major fracture. Okay. So what we often tend to do with this technique is we configure multiple repeats at various different loads, and then we perform some statistical analysis on the resulting data in terms of the scale of the depth of the initial impact event, in terms of the depth of the final impact event, etc. And actually, I think in another part of today's session, some of that results analysis will be covered. So we've got about another 50 seconds to complete, and then what we will do is we will move the sample back to the optical microscope, and we'll be able to take a look at our impact test site and actually look at the fracture that fracture event that's taken place. this technique is not really limited to use with just hard coatings on metals. You could work with even bulk materials. We've done some very successful work recently here with bulk tungsten carbides, for example, to study fatigue performance. Okay, so that's the end of the test. So what will happen now is we'll get an option in a moment to leave the sample where it is or return it to the microscope focal plane. Once it's back at the focal plane, we can go straight across to the microscope and we can take a look at the damaged site. So the sample is just returned to the initial position. Okay, so we just click on this button here, yes, to return to the focal plane. Okay, so then we can just acknowledge the test schedule is complete, and then we can move to the microscope by simply clicking on the microscope icon, and over it goes. And there it is. There's the impact site. The damage is what you might call unambiguous. Some really large, chipped, removed pieces of material all the way around that impact site. So that basically concludes the practical part of the demo of impact testing today. Hopefully we'll have another video for you soon, but in the meantime, thank you very much for your attention. Bye-bye.
So there's the demo completed. So I'd just like to thank Adrian Harris and Andy Bird from Micro Materials for recording of that. Fantastic demo of the nano-impact platform. So move on to what I'm going to do quickly now is see we've got some questions during the video, which is fantastic. We'll come to those in a moment. I'm just going to talk a little bit about some of the analysis methodologies that are used for impact testing. So generally, impact is it's still an emergent technique. There's still a lot of work being done with this, but generally, three important impact metrics are time to failure, so time to that drastic increase in impact depth correlating to a severe cracking event, the final depth reached, and then the final depth minus depth after initial impact. So what is the difference between the depth throughout the impact cycle? So you can compare these, how these change for different samples or with different applied loads. So I have a nice example here of a repetitive impact on alumina with a cube quarter indenter, so quite sharp indenter. So we have there is, so what we see is we get a pre-impact static contact. So when essentially the indenter is just placed on the surface with an extremely small force, then we have our first true impact. What we see is this, we have, as Adrian talked about in the demo, this sort of initial fatigue region as we get, as our impact and as our depth kind of levels off at first. And at that point there, we can then see an extremely drastic increase in impact depth correlating to a failure event. And we can look at the time for this, and then we can see what happens as this impact depth increases across the entire impact cycle. So this is 300 seconds, 5 minutes of testing. So typically we'll do, it's 2 seconds on the surface, 2 seconds off. So 4 impacts, this is 75 impacts in total, which is quite standard as a lot of impact testing goes. But again, this impact, total impact time can be tuned to, whatever it is you want to test. Excuse me. So going on to talk about some of the automatic scheduling of the test matrix. So like we were saying, you'd normally pick a reasonable amount of spacing so that you're not impacting over any sites you've already deformed or fractured, and ensuring that you get a lot of repeats. So you normally do, several of, each different load. So as we have here, 10, 15, 20, 25, 30 on different duplex optical coatings on glass. So this 50 micron spacing is quite standard, used quite a lot for a lot of nano indentation scheduling on the same platform as well. Nice 50 micron spacing. Make sure that you're not sort of testing over an already tested site. And then we can see with this sample, it's these type of fracture events are quite load dependent. At our 10 millinewton load, we see very little. Fracture. We can see in terms of statistics. Again, this can be these tests can be done with far larger repeats, should you want that. We see some fracture events at 15, going up to all fractured at 30 millinewtons. We can also look at sort of fatigue conditions with this, so generate types of SN curves, so like on DLC coatings. So at our higher load, we have very fast failure with our ACH, hydrogenated amorphous carbon, and silicon doped hydrogenated amorphous carbon, but our graded ACH performs far better. We have much longer time to failure when you bring that load down. This time to failure is increasing drastically. With final impact depth, generally what you'll see is when you do start getting fracture occurring, you'll see far more variability in your impact, because you might be shearing off parts of your coatings depending on the actual mechanical properties itself. So these could be parts that could get stuck in the actual impact site. Essentially your cap could shear off and end up in there. So these are all things to consider. But generally, what you'll see is that for this we have a nano multi-layer coating versus our cemented carbide substrate. What we see is from 1.5 newtons onwards under micro impact, so slightly larger load. We see this deviation in final impact depth and failure with this variability. Okay, so now we'll do some questions. So I'd like to welcome Professor Ben Beek from Micro Materials. Hi, Ben.
Hi, Sam.
Well, okay, so let's go through the questions. So I had a few from earlier that I didn't quite get the chance to answer. So we'll go, although I think some of these will be quite useful for you to answer, actually, just because you're familiar with the thermal barrier coating discussed earlier. So I have a question of how would the column or morphology shown for the thermal barrier coating impact its performance?
Well, essentially, it provides a certain amount of strain tolerance, essentially. So and then when an impact occurs on a certain column site, it's restricted within that column site. But when there's sintering between the columns, then it allows the cracking to laterally propagate, essentially, and that then can lead to removal of a larger amount of material, increases the wear rate and the erosion rate, essentially. So that's what you see in practice. So you want to limit this sintering if you can.
Okay, thank you. Let's get another question here, I think from earlier. So how would polishing improve the fatigue resistance? I have an RA of 70 nanometer surface roughness on a well-polished cylinder liner. So in terms of fatigue resistance, I guess the one thing you don't want for fatigue resistance, excuse me, you do want a reasonable amount of stress on the surface, because what this is going to do is stop cracks forming. So some compressive stress is useful, as well as having I'd say a lower surface roughness would be useful. Lower roughness, less likelihood for fracture of other third body particles, and less cracking. Unless there's anything you'd like to add on that, Ben? Or
yeah, I think if you've got too much roughness, then you can have stress rise that acts like essentially stress risers.
Yeah,
obviously can be detrimental, but it can be a little bit complicated.
Yeah, this all gets into the sort of thing of like, fatigue and fretting resistance is a big one where, yeah, it's a compressive stress is useful, but yeah. Moving on, we have another question here. What's the effect of heat treatment of thermal barrier coating on the fracture toughness? So
that's a good question. I don't know off the top of my head. I think typically it does decrease a bit. I'm not completely sure of that.
Okay. Thank you. Okay, so got it. Let's see if I had another question. No, so got a couple of questions on the NanoTest platform here. So I have one. Does the software have any methods to overcome issues with surfaces that are not perfectly flat, i.e. the space between the sample and the indenter/focal plate comes closer or further away as you move away from the initial start point in the array?
Well, there's a couple of features that it does have. One is it has a large measurement range, and the other advantage is essentially that there's a pre-contact and the probe is coming, so the sample is always put at the same position essentially, and in the pre-contact when it comes in. So this sort of minimizes the effect. So actually, the large measurement range means these things are not issues. You have to have really, really extreme differences in across the surface for that to be a problem, and it practically doesn't happen. As Adrian showed right at the beginning of the demo, we can set up for multiple samples with different heights without any great problem.
Yeah, just the retraction distance from the surface has to be set up correctly, and then just the platform will adjust for whatever the reference surface is at that particular time. So yeah, it's quite good. So I have a question here. Hello, is it possible to measure modulus or hardness of soft hydrogels in liquid environment with the nano indenter?
Yeah, no, it certainly is. It's certainly a challenging environment, but the NanoTest has this intrinsically low spring stiffness, which allows it to detect contact more accurately, and that gives it a big advantage over other nano indenters on the market when it comes to detecting contact accurately on soft hydrogels, soft or compliant hydrogels. Because otherwise, on other machines, essentially they got much stiffer frames. So essentially, when they make contact, you just don't detect it at all. So the NanoTest has this distinct advantage when it comes to dealing with these very, very soft samples.
Okay, great, thank you. I think that's it for our questions there. So thank you very much, Ben, for answering those questions there. So okay, so come on to our final slide here. So I just wanted to say thank you everyone for joining. I just want to say this is a new event type for us. So please, if you have any feedback, you can email me, sam@surfaceventures.org. Any feedback from or anything you think would be could do better would be great. Please check out our website. Please share with your friends and colleagues that you think will be interested in this. We do monthly webinars. We'll be having these workshops. I like to just sort of to send people. Please go ahead and you can visit our website. There, have that link. Okay, thanks all. Just do so surfaceventures.org, guys. So just do. Please also visit Micro Materials as well. Micromaterials.co.uk. You can see some further details on the instruments. There's quite a few different test techniques that the NanoTest platform can do beyond just impact testing. So please do take a look at that. Okay. Though it's on screen, and you can find the registration link on the website. You can find the registration link is right there for the next webinar. So please go ahead, take a look at that. Please register. Please share the link again. And finally, as I talked about earlier, we'll be having another workshop. So 10th of June, 9 a.m. British Standard Time on tribology, wear, and damage mechanisms. So again, pretty similar format to this. So again, if you're working with tribology or curious about tribology, please go ahead and join. Send this to your friends, colleagues, fellow students that you know. Go ahead and do that. Okay, so that is all from me, guys. So thank you very much for joining in today, and I'd like to wish you a good day. Stay safe, and I'll see you in the next workshop. Goodbye.